Okay, welcome to the fourth Math 2417 review. Today we're going to go over the mean value theorem. Just to review it really quick. We'll talk about increasing and decreasing functions in the first derivative test. Then we'll move on to concavity and the second derivative test. And last we'll talk about some limits at infinity. So let's go ahead and jump right in with a brief review of the mean value theorem. And if we can recall, the mean value theorem states that if f is continuous on a closed interval from a to b, and f is also differentiable on the open interval from b, then there exists a point C so that our first derivative at that point C is equal to f of b minus f of a over b minus a. And what that really means is our derivative at some point on this interval is equal to the average slope. So if we wanted to really quickly do some example, we could have the f of x is equal to the sine of x on 0 to pi. Oops, want that closed. Okay. First off, we can see f of x is continuous on this interval and also differentiable because sine is continuous and differentiable everywhere. So then our first derivative is equal to the cosine of x. So by the mean value theorem, we're looking for some point C where the cosine of C is equal to f of pi, which is sine of pi, which is 0 minus sine of 0 divided by pi minus 0, which equals to 0. So we're looking for the point where cosine of C is equal to 0, and that is C is equal to pi over 2. So by the mean value theorem, the point C is equal to pi over 2 is where our first derivative, f prime, is equal to the average slope. Now, why don't you go ahead and try out a couple of problems. F of x equals to the square root of x on 1 to 9. Let's see what else. Okay. Go ahead and try these problems out. Just put something in the chat once you think you've got answers. Yes, this is the weekly review. You're in the right place. Right now we're just working on a couple of practice problems regarding the mean value theorem. So essentially what we're trying to do, no problem. All right. I think let's actually go ahead and go over these two problems really quick. Just to be sure you guys can see my screen, correct? It's all black. Ah, interesting. Okay. And there it goes. 1 second. Okay. All right, thank you. Let's see, I guess we'll go ahead and go over this first problem. So our goal is to find a point such that f prime of c is equal to f of 9 minus f of 1 over 9 minus 1. The square root of 9 is 3, and the square root of 1 is 1, and 9 minus 1 is 8, so that is 2 over 8, which is 1 over 4. Or in other words, we're trying to find a point C, the derivative of f of x. This is like x to the power of 1/2. So the derivative of it is equal to, by using the power rule, we would have 1/2 times x to the minus 1/2, which is equal to 1 divided by 2 square root x. And that is equal to 1/4 if we let this x be our c value that we're looking for. So then simply by cross multiplying, we get that 4 is equal to 2 square root c. So c is equal to, that would be 2. That would be square root c is equal to 2. So c is equal to 4. Make sense? Great. Glad to hear it. Okay, number 2. What do you guys think for this one? Any ideas? It's kind of like Rolle's theorem, but it's the converse of Rolle's theorem. If you know what the converse is, basically we took Rolle's theorem and we kind of flipped it around. So instead of starting by saying that our average slope is 0, we're ending by concluding that our average slope is 0. So I'm wondering if this statement is true or not. So you might want to think about cases that might not make it true. And if we broke it down, you could see that what it's saying is there is a point in our interval where the derivative is equal to 0. So does that mean that our average slope on our interval is 0? Okay, we've got two different answers. Actually, the correct answer is no. Let's see. Here, looks like it's kicking me off of screen sharing. Give me 1 second. Okay. The correct answer is no. And the reasoning is, in order to satisfy this first condition, that there's a point where our derivative is equal to 0, we just need to have some spot where we have a horizontal tangent line. So, for instance, consider the function x cubed. It just looks like this, right? And in fact, we have a horizontal tangent right here at y is equal to 0. However, if we took our interval from a to b to be from, I don't know, -1 to 1, you can see that clearly our ending point isn't the same y value as our starting point. So it satisfies this first condition, point where our derivative is equal to 0, but not the second, so this statement is false. Okay, and I think we'd actually, second. Yeah, glad to hear it. Let's actually do a couple more conceptual questions with the mean value theorem, just because I think they're good to think about. Our next one is actually going to be, okay, why doesn't Rules theorem apply to this function? F of x is equal to 0 at x is equal to 0. 1 minus x for 0 is less than x is less than or equal to 1 on the interval from 0 to 1. Lastly, okay, why don't y'all think about those for a couple of minutes and then just put in chat whenever you think you've got an answer for either of them. You don't have to wait until you get them both. reasoning for C is that f of A is not equal to f of B. Not quite, because if we look at this, we can see, and we'll go ahead and say, we can see that f of 0, by our function definition, is 0, and f of 1 is equal to 1 minus 1, which is also 0. So it's not that it's f of A is not equal to f of B, because they are. The correct answer is that it's not continuous, which I see you just said. And you can see that if we actually graphed our function, we would have a point at the origin, and I'm not drawing the axes for, just so you can see what I'm drawing. And then we would have a hole at 1 sloping down to this 0. So if this is 0, 0, the origin, and this is 1, 0, you can see that we've actually got a discontinuity right here. It's not continuous. And that is a requirement for Rolle's theorem to apply. So because it is not continuous, Rolle's theorem does not apply. All right, good. Do either of you have an answer for part D, or question D, I guess? No. All right, that's fine. So let's go ahead and talk about this one. We know that there's a function. Go ahead and graph it out. F of minus 2 is equal to negative 2. And also f of 2 is equal to plus 6, which is about up there. But then we also know that our maximum slope is, or our slope is always less than 1. So if we actually assumed that our slope is equal to 1 for all of x, then we would actually get a point going up like this in a linear function, which means if you can see f of 2 would actually be equal to positive 2, which is less than 6, right? But we actually assumed that f prime of x is bigger than it actually was. So that means that our f of 2 value has to be smaller than this 2 we got from assuming a larger slope. So our f of 2 value has to be smaller than 2, which is in turn smaller than 6. Does that make sense? All right, good. Yeah. So essentially what's going on is we have a function, and or at least we're trying to find a function so that we have one point at negative 2, 2, and another one all the way up at 2, 6. But then we also know that our first derivative is always smaller than 1. So if we assumed that our first derivative was equal to 1, then the highest we could get by going over 4 from this negative 2, 2 up to positive 2 would be by going up 4 as well, if we assumed that f prime was equal to 1, because that would be the biggest slope we could possibly get. That would only get us as far as 2, 2. But that is actually smaller than the 6 value. And in reality, our slope is actually smaller than this one that we assumed it to be. So the real value of f of 2 has to be smaller than this 2, which is in turn smaller than the 6. So we actually cannot have a function that satisfies these conditions, because the slope is not big enough to get our function from this -2 up to this 6. All right, great. Now, I think that's enough of the mean value theorem. So let's go ahead and move on to our increasing and decreasing functions and the first derivative test. And the big thing to remember, I'm just going to write increasing and decreasing functions. And the really key thing to remember here is that the derivative is equal to the slope. And this is a really key concept you'll come across a lot. Highlight this. It's important to remember this because it makes a lot of things we do in calculus make more sense. So for instance, if we were looking at a function and trying to figure out if it's increasing or decreasing, we can say if the first derivative is smaller than 0, our function is decreasing because it has a negative slope. If our function is equal to 0, it is constant. And if our first derivative is greater than 0, it is increasing because it has a positive slope. And the way we can use these rules to figure out where a function is increasing and decreasing is by looking at where our function switches from having a negative slope to a positive slope. Or in other words, we need to look for some points where our first derivative switches from negative to positive, and that will always happen when it crosses over 0. So the points where f prime of x is equal to 0 are called critical points. But another thing that can happen is our first derivative could be undefined, and it could switch from negative to positive. In that case, for example, if you had 1 over x as your first derivative, then for x is -1, you would have our first derivative be 1 over -1, which is -1. But for x is +1, you would have 1 over +1, which gives you a +1. And it actually switches over where this function is not defined. So where x is 0, because you can't have 1 divided by 0. So our critical points are points where our first derivative is equal to 0, or our first derivative is undefined. So the first derivative test is essentially, if we look at our critical points, let's say we found a critical point. Let C be a critical point. Then if f prime of x switches from negative to positive, C is a local minimum. And if f prime of x switches from positive to negative, C is a local maximum. And lastly, if f prime of x does not switch signs, it is neither. So in order to kind of show you what's going on, I'm going to just go over a brief example. Let's say we have a function f of x equal to x to the fourth plus 1 divided by x squared. First, we need to find our critical points, which are where our first derivative is equal to 0. And to do that, we need our first derivative. So to find our derivative, we're going to be using the quotient rule, which is the low term multiplied by the derivative of the top term minus the top term times the derivative of the bottom term, all over the bottom term squared. And if we simplify that, we get 4x to the fifth minus 2x to the fifth minus 2x over x to the fourth. That is equal to 2x to the fourth minus 2 over x cubed. And if we went ahead and set this equal to 0, we can look for points where either this one is 0 or undefined. So right away we can tell if our denominator is 0, our function is undefined, so one of our critical points is x equals to 0. The other way our function could have a critical point is if the numerator is equal to 0. So to do that, we set 2x to the fourth equal minus 2 equal to 0. So 2x to the fourth is equal to 2. X to the fourth is equal to 1. So x is positive or negative 1. So we have 3 critical points right there. X is 0, x is 1, or x is negative 1. And now we just need to figure out the behavior of our first derivative around these critical points. We need to look for sign changes. And I like to use a number line for this. We've got negative 1, 0, and positive 1. And all we need to do is look at what the sign of f of x is. For instance, if we plug in negative 10, obviously our numerator is going to be positive because this x to the fourth is going to make a positive term. But then our denominator is going to be negative. A positive numerator and a negative denominator results in a negative number. Now at x is equal to 1/2, then our numerator is negative, but so is our denominator. So we end up with a positive. At x is equal to positive 1/2, again we have a negative numerator, but this time a positive denominator. So we end up with a negative result. And lastly, for x is bigger than 1, everything is going to be positive. So now we can kind of see our behavior of our first derivative. So by the first derivative test, we know that if our derivative changes from negative to positive, we have a local minimum. And if our function switches from positive to negative, we have a local maximum. So right here, our function switches at -1 from negative to positive. So we have a minimum. And at 0, it switches from positive to negative. So we have a max. And at 1, it switches from negative to positive again. So that's another minimum. And one way you can think of it is if you just saw generic negative and positive slopes, you can actually kind of see that it would kind of make a valley right here to come down at a minimum, make a mountain at 0 to have a maximum, another valley at 1. So we could write f of x as local minimums at x is equal to -1 and 1, a local max at x is equal to 0, and we can also say where x is increasing and decreasing, because if it has a negative slope, it's decreasing. So f of x is decreasing wherever its derivative is negative, which is negative infinity to negative 1, as well as 0 to 1, and it is increasing on the intervals where its derivative is positive, which should be negative 1 to 1, sorry, negative 1 to 0. I cannot write negative 1 to 0 and 1 to infinity. Make sense? All right, great. So we'll go ahead and do a couple of brief practice problems. First one. So suppose I should give you instructions. Find where function is increasing or decreasing, and where local extrema are, so where its maximums and minimums are. Just the x value, I don't need the y values. First up, no rationalizations. Ooh, that's the first one I had planned out, so then I believe the second one was sine x cosine x plus 5. Giving you trig as well, I know. And lastly, I had this one combines the two. Lucky you. Sine x over 1 plus cosine squared of x. Enjoy! All right, I'll give you a couple of minutes to try those out. For sake of time, I think I'll probably only end up going over one of them, so I'll let you choose which one I go over. Oh, and I think I'm going to add a couple of constraints just so you don't have to pay, because these trig functions should essentially repeat that point. So just look at 0 to pi, and again 0 to pi. All right, how's it coming? Good on B. All right. Give you a few more minutes, just making sure you weren't stuck. All right. I think I need to get going if we want to make it through the rest of the content. I'll get the answers for two of them and then just solve the third one. First one is increasing on negative infinity minus 1 over root 2 union positive 1 over root 2 infinity, and then it's decreasing on negative 1 over root 2 to positive 1 over root 2. And it has max at negative 1 over root 2 and a minimum at positive 1 over root 2. The second one, I think will actually work out because it's actually pretty simple and straightforward if you just use a trig identity from the start. The identity I'm going to use is that 2 sine of x cosine of x is equal to the sine of 2x. In this case, we've just got a sine of and not a 2 sine cosine. So I'm going to multiply both sides by 1/2. So our function is actually 1/2 sine 2x plus 5. And if we take the derivative, that's easy enough. We just take the derivative of sine is cosine times the derivative of the inside, which is 2. That can neatly with our 1/2. So our derivative is just cosine of 2x. And it's equal to 0 when x is equal to pi over 4 and 3 pi over 4. And cosine is bigger than 0 from 0 to pi over 4 since you've got the 2x on the inside, or it's increasing on 0 to pi over 4 as well as after it crosses over at 3 pi over 4 all the way up to pi. And it's decreasing in between that, so from pi over 4 to pi over 4. So that would mean that it has a max at pi over 4 and a minimum at 3 pi over 4. The way I thought of it is I thought, well, I know that cosine is equal to 0 at x is equal to pi over 2. So when it's halfway to pi over 2, cosine of 2x will be equal to 0. So that will be at pi over 4, and I know that it switches from positive to negative at that point. That's why we have a maximum there. And I knew that the opposite happened. It switched from negative to positive at 3 pi over 2, but half that we got 2x, so 3 pi over 4. And then I just created my increasing and decreasing intervals from that. Does that make sense? All right, and then part C is, it's just essentially the derivative. You can simplify it some with trig rules. Your derivative eventually comes out to 2 cosine of x divided by 1 plus cosine squared of x squared. If you simplify the numerator using some trig identity, essentially this is equal to 0 only when your numerator is equal to 0. This denominator is never going to be equal to 0 because you have 1 plus this cosine squared, so that's always bigger than 0. So essentially the only part we need to be careful of is when x is equal to pi over 2. So cosine again is positive from 0 to pi over 2, so we're increasing on that interval, decreasing after that, and that means we have a maximum at x equals to pi over 2. All right, moving on, we come across next topic is concavity and the second derivative. So our first derivative tells us the slope of a function or the rate of change of a function. Our second derivative tells us the rate of change of the slope. And it's kind of weird to think about, but if you want to consider it, we really have two ways that concavity look. First off, it can be like upward curving thing, kind of like a bowl shape. This is called concave up. And this occurs when f prime, double prime of x is bigger than 0. We can also have concave down. And this is when our second derivative is smaller than 0. And if it doesn't make one of these curve shapes, if it's just like a straight line, even if it's still increasing, this has no concavity. And this occurs when our second derivative is equal to 0. And an example of when we might see no concavity is if we just had, again, like a linear function, 2x plus 3, our first derivative is equal to 2, then our second derivative is just equal to 0 as the derivative of a constant. Okay. Then our second derivative test says if C is a critical point, then if f double prime of C is bigger than 0, we have a local minimum. And the reason being, when we have this greater than 0, that means we have a concave shape. So our minimum would occur at the bottom of that bowl. And if our second derivative at that C is smaller than 0, we have a local maximum. And again, that's because if we would have a point at like the top of a hill, like that. And again, if our second derivative is equal to 0, that means we have neither a local maximum nor a local minimum. One important thing to notice is we can either have a local we can have 0 concavity on a linear function like this, or where a function switches from concave up to concave down, like the x cubed function, for example. We've got something that goes like this. You can actually see we've got this downward curved part on the left-hand side and an upward curved portion on the right-hand side. It's actually concave down on the left and concave up on the right. So at exactly 0 right between them, it has no concavity because that's where it switches between up and down. So for example, let's say we have a function x equal to negative 3x to the 5th plus 5x cubed. Well, in order to determine concavity and maximum minimums, we need to find our first derivative, negative 15x to the 4th plus 15x cubed. That's negative 15 times x to the 4th minus x cubed, x squared, sorry. And to find our point C where this is equal to 0, we just set it equal to 0. So then x to the 4th equals to x squared, which occurs at x equals negative 1, 0, and 1. We also need to find our second derivative. And to do that, we can just take the derivative of the first derivative. So that's negative 60x cubed plus 30x, which is negative 30 times 2x cubed minus x, which is negative 30x times 2x squared minus 1. Just like that. And in order to determine whether these points are maximums or minimums, we can plug them into our second derivative. So our second derivative at negative 1 is negative 30 times negative 1 times 2 times negative 1 squared minus 1. And we're really only interested in whether the second derivative comes out as positive or negative. This negative 30 times negative 1 is positive. This is a 2 minus 1, which is positive. So it's positive. So because it's positive, it's concave up, which means we have a minimum at x is equal to 1. If we plug in 0, well, here we get negative 30 times 0 times something else. We don't really care because of this 0, it ends up being 0. So because it has no concavity, it is neither a max nor a minimum at x is equal to 0. Lastly, we have f is equal to 1. That should be the second derivative. That's negative 30 times positive 1, and then 2 times 1 minus 1. This is negative times a positive, which is negative. So we have that should be a concave down portion. We have something that's concave down. So we have a maximum at x is equal to 1. And there, that is how we found our maximums and our minimums. Make sense? All right, great. The roots of the second derivative mean. The roots of the second derivative, so where f double prime is equal to 0. All right. Essentially, all right. This is where we have, again, no concavity, and that's where the concavity changes, right? It's similar to the first derivative, where it switches from going to increasing to decreasing in our function. Instead, with the second derivative, we just have it switching from positive concavity to a negative concavity, or concave up to concave down. It can look like a lot of different ways. You can think with like your sine function. It happens at x is equal to pi, or with, again, a lot of cubic functions, it's always going to happen somewhere in the middle, or with various other polynomials. It's just wherever the second derivative is equal to 0, that's where you have a chance of having a concavity change. Because if you think of like the quartic function, f of x equals to x to the 4th, our second derivative is 12x squared, which is equal to 0 at x is equal to 0. But the graph just looks kind of like this, and we actually don't have a concavity change. Because, as you can see, if we drew out a number line for this, on both sides of 0, our second derivative is positive. So that means it's concave up this side, and it's also concave up on this side. So that's kind of what it means when our second derivative is equal to 0. We have a chance of having a concavity change. Why don't you find the maxes and minimums of this function f of x using the second derivative test. And the function is going to be negative x cubed plus 7x squared minus 15x. All right. I think I'm going to have to go over this just so we can cover the last topic, which isn't super hard, but we should still cover it a bit. So in order to find our maximums and minimums, we first need to find our critical points, which are where our first derivative is equal to 0. And we get this function here as our first derivative, and we need to solve for where it is equal to 0. I'm going to use the quadratic formula. So we get minus 14 plus or minus 196 minus 4 times a times c. So that is 3 times 15 times 4 is 180 all over 2a. This is negative 14 plus or minus the square root of 16 is 4 over negative 6. Negative 7 plus or minus 2 over negative 3. So first off, we would get negative 9 over negative 3, which is positive 3 as one of our roots. And second, we would get negative 5 over negative 3 as the second of our roots. So that would just be a positive 5/3. And then we would simply plug that into our second derivative, negative 6x plus 14. We plug in a positive 3, we get negative 18 plus 14, which is smaller than 0. So that would be concave down, so it is a max at x is equal to 3. And at 5/3, our second derivative is negative 6 times 5 over 3 is negative 10 plus 14 is bigger than 0, so we're concave up. So we have a minimum at x is equal to 5 over 3. Okay. Last topic is limits to infinity. And these are really fairly straightforward. We have some kind of polynomial function. This is all from this week. According to the syllabus, technically, but I'm assuming you've gotten kind of off the syllabus. I typically just follow the syllabus, and I don't really have super detailed lesson plans of what your professors are doing, so I just try to guess it as much as I can. Have you been talking about limits to infinity in your class, such as like the limit as x approaches infinity of 4x cubed plus 2 over 5x cubed, stuff like this? Class is kind of behind. Yeah, I think that's a fairly common in the online situation. But these limits to infinity really aren't all that bad if you've got a rational function. Plus x squared minus x. All we do with these limits to infinity is we essentially just look at the biggest terms, the terms with the highest power. So in the top, we've got the 4x cubed, and on the bottom, we've got the 5x cubed. Anything that's not these highest power terms, because this x squared is it's a smaller power than the x cubed, we can basically just ignore it. And then we just look at the powers. On top, we've got a 3. On bottom, we've got a 3. Since 3 is equal to 3, we just compare the coefficients. That's what we do for balanced powers on top. If we have a limit as x goes to infinity of something like x squared plus 2 over x cubed minus 1, again, we look at just the biggest term on top and the biggest term on the bottom. We notice that our bottom power is bigger, right? 3 is bigger than 2, so our limit goes to 0. And we call this bottom heavy. And lastly, we've got the limit of a top heavy function, which, as you might assume, is where the power on top is bigger than the power on the bottom. In this case, we would say this limit goes to infinity for a top heavy function. With these top heavy functions, they could also go to negative infinity. For instance, if we had a negative in front of this x cubed, that would make it go to negative infinity. But the big thing to remember is if the top is of a greater order than the bottom, if it's top heavy, we're going to have it go to positive or negative infinity. Here's a couple of brief practice problems. Let's say you've got 4x cubed minus x squared over x squared plus 3. And these are all just the limits as x goes to infinity. So I'm probably not going to keep writing them out. That 4 over 5 is considered a horizontal asymptote. you are correct in that assumption by saying that, because as x goes to infinity, the function value approaches 4 over 5. That's the definition of a horizontal asymptote, essentially the limit as x goes to infinity if it approaches some real number. So for instance, a 0 or some constant like 4 over 5. All right, just try those three out, and whenever you get an answer, just holler it out in the chat. Infinity, 0, and 3 over the square root of 2. That is correct. For this first one, we can see we've got a top-heavy function, so its limit is infinity. For the second one, we've got a bottom-heavy function, so its limit is 0. And lastly, for this third one, it might look bottom-heavy at first, but you have to consider that we've got the square root of an x squared term, so this actually has the same power of x to the first, essentially, as this numerator. So we need to look at the coefficients, and in that case it's 3 divided by, we have a square root of 2. So 3 divided by the square root of 2 is our answer for that one. All right, that just about does it for this review. So I'm going to go ahead and